All right, so more about fake plateaus. Another thing that might come to your brains as you're wrapping them around this stuff is, okay, so I said that this was a result of having, remember I wrote it, non-positive data. And if you only have positive data, it will always approach it from above. You'll never have a local maximum or minimum. And so you'll know whether you're actually stuck in a local maximum or minimum, or if you've actually reached a plateau. So you might think, okay, let's just use positive data. There are issues with that in regards to what operators you can write down. And again, we'll talk about operators later. We'll talk about that in the next lecture. So there are reasons for having non-positive correlation functions. But even more generally, did I have a picture for this? No, okay. That's fine. So even more generally, if you think back to this thing we're trying to extract data from, so what I've shown here is actually the effective mass for delta E. So it's the effective mass for the 2-nucleon energy minus twice the single nucleon energy. And this is necessary for actually seeing a signal because these correlated differences between the energies is the only thing that allows us to see something different from non-interacting. So let me just write that down. So the thing we look at is the ratio correlator. And so this is the 2-nucleon correlator divided by the single nucleon correlator squared. And so this, as t goes to infinity, falls off with the energy of the 2-nucleon system over twice the mass of the nucleon. And so this goes like e to the minus delta E times t, where delta E is the so-called interaction energy. So it's the energy associated with non-zero interactions. And if we look directly at this ratio, it gives us the correlated difference between the two energies if you were to fit each of these correlation functions independently. And you can do that as well. You can fit them independently and then take a correlated difference using jackknifing or whatever way you want to propagate your correlated uncertainties. But the problem remains that the thing you're really looking at is not an individual correlation function, but the ratio between two correlation functions. So where can we see that? So if we look at including just the first excited state into this ratio, so let's say, so we're looking at CNN over CN squared. That is a squiggle. Okay, so let's say I'm going to put in my overlap factors as just A and B, etc. So I'm going to include the first excited state. I'm going to call that prime. Prime does not mean derivative. It just means something different. And then in the denominator, oh wait, hang on. to square it after I'm done. Then we also get some excited nucleon mass, and I'm going to square that. Okay, so now I can pull out a factor of this. I'm going to get a c squared e to the minus 2 mnt. And then I get 1. This, and then this will be, say, some delta prime, which is the difference between mn prime and mn. So I'm just going to use a lot of deltas. Just keep in mind that the scale of the deltas is smaller than the scale of these energies. So deltas just refer to generic energy differences. Okay, this is squared. All right, so now I have something that I can expand. So this term is much smaller than 1, so I can expand this denominator. Yeah, I need more space. Okay. Okay, so this guy goes like, this is just copying down the numerator. And then I have this thing I pulled out. And I'm going to bring it up top. So that's just this. And then I'm going to expand this, assuming that the second term is small. I'll write it down here. And then higher order terms. Okay. So, and then let's just finish this just to make it clear. So I'm just going to distribute this guy into there. And that gives us our delta, which is the difference between ENN and ENN and twice MN. So this is the thing we're trying to extract. That's squared. This is going to be a double prime because it's just a different delta. And then 1 minus this. Oh, whoops, I called this guy. That one I already defined. Okay, plus dot, dot, dot. Okay, the point being, we've now introduced this minus sign. So even if all of our overlap factors, A, B, C, and D, are positive, by looking at the ratio, I've now introduced the potential for having terms with different signs that can contribute to give this near cancellation that can lead to fake plateaus. So this is the concern. Unfortunately, it's kind of necessary to look at these ratios because we can't just extract the energy difference without constructing this correlated difference between them. But in this way, we are introducing this potential for cancellation between states. I should note, however, that in order to have this cancellation for this local minimum, we have to have terms that are all contributing at roughly the same time, right? So if, let's see, so here, for example, so at t equals 10, say, in order to get this local minimum, I have to have cancellation between multiple terms that are of roughly the same size at this time. And so this won't occur if these deltas are all very different from each other, because then the different terms at a given time will not all contribute in order to produce this cancellation. So that is one caveat. In order to really assess whether you think there might be a cancellation between terms, we should be more careful in looking at the different deltas, because these are differences in energies between different types of excited states, and we'll talk about that some more the next time. So I will end this lecture here, and we'll see you in lecture 3.